Welcome to the next lecture of AC circuit analysis, in which we are going to see apparent power and power factor. We know that the voltage and current applied across some circuit element are given by Vm cos of omega t plus theta v and Im cos of omega t plus theta I, where theta v and theta I are the phase angles and Vm and Im are the peak values of the voltage and current signals respectively. So from our previous knowledge, we know that the average power is given by half of Vm times Im times cos of theta v minus theta I, and if we put the value like Vm divided by square root 2 and Im divided by square root 2 by splitting this 2 into square root 2 multiplied by square root 2, then we get the RMS value instead of this Vm, and half value will be removed. So in this case, the RMS value of voltage and current multiplied by the cos of theta v minus theta I will result in this relationship where S is known as the apparent power, which is actually the multiple of RMS value of current and voltage, and this cos of theta v minus theta I is called as the power factor angle, which is nothing but cosine of the phase angle between voltage and current. So simply writing, we can say that apparent power is the multiple of RMS value of voltage and current through some circuit element. The average power is the product of two terms, and it is no those two terms are the apparent power and the power factor. Apparent power is normally measured in volt ampere to distinguish it from the other power quantity. There is no other reason, because we are multiplying in actual the voltage and current, so it's volt and ampere, the units for voltage and current, so it should not be confused with anything. And we as a matter of convention, we represent apparent power in terms of volt ampere to differentiate it from the real and imaginary parts of the power, which we are going to see shortly in this lecture. So the next is the power factor. Power factor is from our previous relationship on this slide. We can see that average power divided by the apparent power would be cos of theta v minus theta I. So, and it is known as power factor. Theta v minus theta I is the power factor angle, and because the cosine of any angle is positive, so we can see that for the range of theta v and theta I, it cannot be negative. The power factor angle is equal to the angle of the load impedance if V is the voltage across the load and I is the current through it. As we have previously seen also, that load impedance Z can be given by Vm theta V divided by Im theta I, voltage across the impedance divided by the current through the impedance. This is nothing but in accordance with the Ohm's law. So here, if we measure the angle of this impedance, this is same as this power factor angle. So alternatively, we can say that if RMS value is equal to this peak value divided by square root 2, this is in terms of phasors. So if here it's phasor, then it is also a phasor quantity divided by 2, and we get that the RMS value and theta v. So in this case, the impedance can also be represented as the ratio of RMS voltage and RMS current through an element, through an impedance, through, and the cosine of or this impedance angle theta v minus theta I. The power factor is the cosine of this phase difference between voltage and current. It is also the cosine of the angle of load impedance. Both statements are equally true and equally valid. So we know that the power factor is P by S, and there because the value of power factor can only range from 0 to unity, we can see different scenarios. For purely resistive load, theta V minus theta I would be equal to 0, because for purely resistive load there is no phase difference between the voltage and the current through and across it. So in that case, this angle would be 0, so cos of 0 results to be unity, so we say that power factor is unity. The apparent power is equal to the average power in that case because of this relationship. This can only be unity when P and S are equal in this relationship. And secondly, for purely reactive load, when there is purely capacitive or purely inductive load, then in that case theta V minus theta I would be equal to plus or minus 90 degrees, and in that case power factor would result to be 0 because cos of 90 is 0. As I mentioned earlier, for the given scenarios we can have only a purely resistive load, purely reactive load, or the mixture of both these components. In all these cases we cannot get the phase difference between voltage and current greater than plus 90 or lesser than minus 90. So in that case we can have only the power factor from 0 to 1. So in that case average power would be 0 because P by S is equal to 0, so S multiplied by 0 would result in an average power of 0. And for the mixed scenario, when we have some portion of the impedance as resistive and some as inductive, then leading power factor would mean the capacitive load, and the inductive power factor means the lagging load. Power factor affects the electric bill consumers pay the utility companies. So power factor is an important part which affects our electricity bill we usually pay. So how will it affect, we will shortly see. So here is a short example of this. A series connected load draws a current I of t equal to 4 cos of 100 pi t plus 10 degrees ampere when applied the voltage of 120 cos 100 pi t minus 20 degrees. Find the apparent power and the power factor of the load. Determine the element values that form the series connected load. So we need to find the apparent power, the power factor of the load, and the element, the resultant impedance along with its values. So in order to get the apparent power, we need to multiply the RMS values of voltage and current. As a matter of convention, the power companies usually represent the current and voltage in terms of RMS values, but here we are not specified anything like that. So what we do is we just consider them as peak values and divide them by square root 2 in order to get the RMS values. So multiplying them will result us to 40 volt ampere, which is apparent power. For the power factor, we have got this theta I and this theta V, plus 10 and minus 20 respectively. So we just put values here and take the cos of the angle. So it's leading because this is negative, and this is negative for the capacitive elements, as we have seen here. Next, we are going to see the impedance value, which is volt upon current, and by putting the values, the the phasor values of the voltage and current can be drawn from these two given values, given functions, and we see that the impedance is 25.98 minus J15, and this negative sign also indicates the capacitive impedance, because the impedance for the capacitor is minus J upon omega C, and for inductor it's J omega L. So here it's minus, so we can directly get a hint that the impedance is capacitive in nature, and this is also obvious from here, the power factor calculations. So in order to calculate the impedance values, this is the resistive part 25.98 and minus J15 is XC, and as I have already mentioned that XC is minus J upon omega C, so equating minus J upon omega C with this minus J15, we can calculate easily the value of capacitor. Omega would be 100 as mentioned in these two relationships. In this way we get the capacitance values of 212.2 microfarad. And same way we can perform this another example where we need to determine the power factor of entire circuit and calculate the average power delivered by the source. So here, in order to get the whole power factor, we need to calculate the net impedance, which would be the series combination of this parallel combination as well as this 6 ohm resistor. So first we need to find the parallel combination of 4 and minus J2, then add it to 6 ohm. We will get the series total impedance of the load, and this angle is negative. This means it's leading power factor, and power factor is cosine of this angle. So in this way we can get the power factor, the first part of our question. Similarly, we can get the RMS values of current like this one using Ohm's law for AC circuits, and with this way we get the RMS value as this one, 4.286 angle 13.24. After that we need to find the average power supplied by the source. So this is the relationship for the average power, which is nothing but the multiple of apparent power and power factor, and apparent power is Vrms times Irms. So with these simple calculations we reach the final answer. There is another important indication that the power delivered by the source is consumed by the load, and we already by the resistive part of the load. So if we take the RMS current delivered to the load, multiply it with the resistive portion of the impedance, what we get is, which is 6.8. From this first calculation we can just reach the similar answer, 125 watt and 125 watt. So this means that whole of the power delivered by the source is consumed across the resistive part. There is no energy or no power dissipated across the reactive parts in ideal scenarios, and that is moving to and fro. The power dissipation in the reactive part is 0, and we are just going to see in due detail shortly. Here the next term, complex power, is used, and we can see that the complex power is the term which is coined in order to have the impact of all different power quantities we have seen so far, and this is the multiple of the voltage and current through the through some element, and this conjugate on the current is nothing but to indicate this negative sign we are seeing constantly in our previous calculations, like this one in power factor angle. This is for mathematical reason, there is nothing else hidden into it. So like before, V and I are usually the phasor quantities in terms of peak values. So if we want to convert them in RMS values, we split this 2 as square root 2 multiplied by square root 2, and then we reach this answer where Vrms and Irms are these quantities, and then multiplying them in such a way we get this whole term. Previously we are just when we are working with average power, this was the only real part of this term, but not the imaginary part of this term. But here we are concerned, or we are getting the imaginary part also in this complex power. So apparent power is similar, which is used for the real or reactive part, but the whole complex power is the combination of both real and imaginary parts of this uh, voltage and current multiples. This equation can also be obtained from equation 9 we have previously seen. However, we are not going into that detail. Listeners and students can perform this on their own also. From this equation, what we get is that the magnitude of complex power is the apparent power, as we have just mentioned that this is the magnitude Vrms times Irms square plus Vrms times Irms square whole under the root is the magnitude of this one, and when we calculate it, it's equal to the apparent power, and it is measured in this due to this the complex power is also measured in volt amperes, and the angle of complex power is nothing but the power factor angle. The complex power may be expressed in terms of the load impedance. Like before, we can perform these calculations Vrms divided by Irms, and when we put the the phasor values, we can get these phase angles. And Vrms can also be written as Irms times Z in terms of Ohm's law, and when we put back the values, we get the complex power as the multiple of Vrms and Irms conjugate. So in this way, the power dissipated across the impedance of R plus Jx would be, the complex power dissipated would be I square R plus J times I square X, where I square R is the real part of the power dissipation and I square X would be the imaginary part of the power dissipation across the load, and real part is the resistance and imaginary part is either inductance or a capacitor. So moving on, P is the average or the real power, depends on the load's resistance. Q is the reactive power, which depends upon the load's reactance, as I just mentioned. And comparing equation 44 and 47, 47 is this one and 44 is this one. When we compare them, what we get is that real part is the Vrms times Irms cos of theta v minus theta I, and Q is the Vrms times Irms times sine of theta v minus theta I. The real power P is the average power in watts delivered to the load, as we just saw in our last example that this is the real power, which is measured in watts. The unit used here is watts for this one. So, and the real power is actual amount of power dissipated across the load. The reactive power Q is measured as is a measure of energy exchange between the source and the reactive part of the load. Because the reactive part do not dissipate any power, but they require some amount of power in order to make the equipment work, reactive equipment work, or we can say equipment with reactive portion work. All the power required by the reactive portion of the impedance would be moving to and fro between source and the reactive portion. So it is not actually dissipated, but it goes back to the source. However, the problem is that we will observe higher line flows in case of the reactive parts of the power. So although the amount of reactive power comes back to the source, but it increases the line flows, and to avoid this, the power companies provide us with certain limit of the power factor. Otherwise, if we have more power factor than that, then the power companies can apply the penalties on the consumers, and consumers need to correct this in order to get themselves saved from the penalties and the problems in the power system. So the unit of Q is volt ampere reactive. This is the unit of the reactive portion in order to distinguish it from the real power. The complex power is until this stage we have seen that there are three different types of power factor: unity power factor, which was for purely resistive load; leading power factor, which was for purely capacitive loads; and the lagging power factor, which was for the inductive portion. And when we have leading or lagging power factor, the some amount of power, which is represented by this Q, moves to and fro between source and load. However, it is not dissipated in the load. The complex power in volt ampere is the product of RMS voltage phasors and the complex conjugate of the RMS current phasors. The complex quantity, its real part is P and imaginary part is Q, as we have already seen. So as a summary, we can say that the complex power contains all the terminologies. Like this is complex power, it contains P plus jQ, where P is the real power, a real part of S, and Q is the reactive power, the imaginary part of S, given by S cos of theta and S sine of theta, where theta is theta v minus theta I in either case. Similarly, the apparent power is the magnitude of this complex power. So complex power actually contains all the information we have already seen. So by knowing and understanding complex power in true spirit, we can understand all these terminologies. And the power factor is P by S, where theta cos of P by S, which is equal to cos of theta v minus theta I. It is a standard practice to represent S, the complex power, P and Q, in the form of a triangle. And from this relationship we just saw on previous slide 43, that S is P plus jQ. We can represent it in vectorial form like this one, vectors P and Q, because real and imaginary part are at right angle to each other. So this is what they represent, and according to the amount of real and reactive part, the S can be deduced. Similarly, and this theta is the power factor angle, the difference of theta v and theta I. So, and as this angle is similar to this impedance angle, so the total impedance can be also deduced from this relationship. So in this way, what we can see is the power triangle has four items: this P, Q, S and theta. P real power, Q imaginary power, S the complex power, and theta the imaginary the angle, power factor angle in that case. So if we want to understand the lagging and leading power factor, this triangle or this part is very helpful. For example, if the lagging power factor theta v minus theta I is positive, then we can see that the complex power is in first quadrant, whereas for leading power factor the complex power is in fourth quadrant for capacitive loads and for inductive loads. It is also possible for the complex power to lie on the second or third quadrant, although it is possible, but this is not always the case. This is not beyond the scope of this course, so we might not be covering that. This requires that the load impedance have the negative resistance, which is possible with active circuits, so it is not the topic of this course, so we will not consider it. With active elements like transistors or diodes or things things like that, we can get the negative resistance, and we need not to discuss it in this course. So the example of complex power is the voltage across the load V of t is given by 60 cos omega t minus 10, and current through this element is flowing in the direction of voltage drop is 1.5 cos omega t. So we need to find the complex and apparent powers and real and reactive powers and the power factor and the load impedance. So proceeding, Vrms is given by the 60 divided by square root 2 with angle of minus 10. The Irms is given by this relationship. So in order to get the complex and apparent powers, we need to multiply both of them, and its magnitude is 45, which is the apparent power, the complex power and the apparent power. Similarly, in order to get the real and reactive part, we need to split this into expand it with Euler's identity maybe, or we can just write it 45 cos of this theta and for j 45 sine of this theta. So in this way we can get the real part is 22.5 and minus 38.97. The power factor is cos of minus 60 z v by I, and 60 by 1.5 would be the impedance. So in this way we can get the nature of the impedance also with this sign. It indicates that it's a capacitive impedance. Another example, a load draws 12 kilovolt ampere, so it's either S or S in either form, complex or apparent power. So because now angle is mentioned, so it's mostly the apparent power, and the power factor is this one. From 120 volt RMS sinusoidal source, calculate the average and the reactive power delivered to the load, the peak current and the load impedance. So power factor is given 0.85, so cosine of this power factor angle, we get one part of the our real power dissipation or average power dissipation across the load, and this is nothing but 12,000 multiplied by 0.85, which will result into 10.27 kilowatt. Similarly, the reactive portion is 6.2 kilovolt ampere. This can be written as kilowatts. Since power factor is lagging, the complex power is P plus jQ because it's lagging power factor. So we just do the mathematical manipulations and reach the final RMS current as this one. Similarly, the load impedance can be calculated by dividing the RMS voltage and current. With this, I close today's lecture. Hopefully, we will see you soon in our next lecture. Thank you very much. Goodbye.